All right. So we've already talked about stress a little bit, but now we're going to actually go into a discussion on the different types of stresses that are applied to bodies and the equations that are used to calculate them. Now, the absolute simplest stresses that we can apply to a body are those that we call uniformly distributed. That means that across the cross section of a body, the stresses are equal everywhere along that cross section. In general, there are two cases, well, technically there's three, but two cases of uniform distributed stress. The first, let's consider that we have a rod or a rectangle or whatever that's subjected to a normal force F, where this force is perpendicular to the surface. And that force is distributed across the cross section of that area. If we were to calculate the stress, sigma, is simply equal to the value of that force divided by the cross-sectional area, where the stress is uniform or equal everywhere along the surface, right? Now, this could be in tension, where the force is stretching the geometry, but it also could be in compression, where the force is compressing the geometry, but uniformly. All right? Pretty straightforward. Our assumptions here, a few assumptions are made. One is that the bar is straight, that the line of action of the force contains the centroid. So it's coincident with the centroid of the geometry. We're loading concentrically right down the middle. And that the section that we're taking to expose those stresses are far away from the ends where we're actually applying the force. All right? Not too bad. The second case that we have for uniform distributed stress is a case where we are exerting pure shear forces to a geometry. This is usually the case when a force is applied across the cross section of a member, such as a beam, very close to a wall or to a support. In this case, the force is being applied almost coincidence to the cross-sectional area where stress would be calculated. So this is the case of pure shear. Under a case of general shear stress, if we're exerting a force that's far away from the support, then we're going to induce bending into the sample, and we won't have an exact uniform stress applied at the wall, right? So that's really the difference, that shear force is applied very close to the support or an interface in a geometry. If we section the pure shear case, the force that we're applying is right on the wall. There is a support force from the wall. There is very little distance between them. And from that, we then assume that we have a uniform distribution of shear stress across that wall, where the shear stress, tau, is equal to the shear force, V, divided by the cross-sectional area, where that shear force is parallel to the cross-sectional area. Now, the assumptions that are made here, we're assuming that this stress is uniform. In reality, it's not perfectly accurate because there is a slight distance between the force that's actually being applied and the support. But in general, this assumption is close enough for us to accept and simplifies greatly the solution to the shear stress. So now we got the two simplest cases, uniform distributed stress, both normal stress and pure shear stress, defined. Next, we'll start to go into some more complicated equations for stress. What happens when stress isn't uniform? What happens if it's linearly distributed or radially distributed? Catch you next time.